This engine requires neither electricity nor gasoline, yet it still performs mechanical work. It works with the temperature difference between Earth and space. And scientists from the US indirectly connected the engine to space via a specially coated plate, which provides a temperature difference of more than 10 degrees Celsius at night. The system uses what is known as radiative cooling and the nearly 200-year-old Stirling engine. The engine is physically efficient, emission-free and theoretically usable anywhere in the world. Today we will take a look at the thermodynamic trick behind the technology, what radiative cooling is and whether it should revive the old Stirling engine. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps and in Germany we say Los geht's! There are now many ways to generate green electricity. Solar cells are particularly popular for private households, but at night or in bad weather, they produce virtually no electricity. Of course, without sun, there is no energy. Such dark times pose real challenges for the energy transition. This means that in order for everything to function at night, for example ventilation or air conditioning in buildings, electricity must either be stored at greater expense or provided in a complex manner. That is why scientists around the world are searching for new ideas. One approach that is currently gaining momentum in research is radiative cooling and how to use it for electricity production. This means that we specifically use the cold temperature of space to send heat from Earth directly into space as if through an open window. I will explain exactly how this works in a moment. So far, this has mainly been seen in new coatings that cool buildings in summer or special films on roofs. But this principle is now to be used to perform mechanical work without any electricity or gasoline. The basis for this is a 200-year-old Stirling engine. The Stirling engine was invented by Robert Stirling in 1816. Unlike a combustion engine, the Stirling engine is a so-called external heat engine, so a device that generates mechanical energy from external heat energy. The heat comes from outside and not from combustion in the engine itself. I'm actually a big fan of Stirling engines. As a kid, my dad once gave me one and it was probably one of the things that got me interested so much in physics that I later studied it. Okay, so let's take a look on how it works. So the principle works like this. A gas, usually air, is enclosed in a cylinder. One side of the engine is heated by a heat source. This can be fire, solar heat, waste heat from an industrial plant, or simply a cup of hot water like in my case. The other side of the engine is cooled, usually not actively but simply through contact with the ambient air. So this is the cool side. And now let's give the engine a little twist. Okay. So the temperature difference between the two plates causes a gas to expand and push a piston upwards. Then the warm gas comes in contact with the cold side of the top. When the gas cools down again, it contracts and the piston moves back. And this back and forth movement of the piston causes a flywheel to turn, for example, and this generates mechanical work. Stirling engines are efficient and quiet. Usually they are quiet. This one is not. I have to put some oil in it. Let's take it down because it's a little bit annoying. And what is especially interesting with them, they work even when the temperature difference is only a few degrees, which is quite unique. Nevertheless, over time they have been replaced by combustion engines and later by electric motors, which are more compact, more powerful and easier to control. But they can be powered by almost any source of heat or even cold. And researchers in America are now taking advantage of this. So let's get to the new Stirling engine. Instead of creating a cold side using air cooling or water, as is usually the case, scientists at UC Davis have connected the cold pole of the engine to space. And you don't need a rocket or anything to do this. What's special about this is that the heat source and the cold source are not located close to the engine, as it is usually the case. Let's take a closer look. So the design consists of two plates as usual. The lower plate is buried about 5 centimeters deep in the ground, connecting the engine thermally to the ground. This means that the heat needed in the engine comes directly from the Earth. The upper plate, on the other hand, points directly into the sky and is cooled by radiative cooling. For this purpose, the plate is coated with a special paint that is particularly effective at emitting infrared radiation. To talk about radiative cooling, we need to take a step back and look at what heat actually is and how it is transferred. Heat is ultimately nothing more than movement, more precisely the disordered movement of atoms and molecules in a substance or body. Physicists call this Brownian motion. There are three ways in which heat can be transferred. Firstly, heat conduction. This occurs when we bring two bodies of different temperature into direct contact with each other. The fast, hot particles collide with the slower, cooler ones and transfer energy in this process. For example, your hand becomes warm when you touch the heater or a hot cup of tea. A second form is convection, so heat flow. Here, heat is transported by the medium, usually air or water. Moving itself, for example, warm air is rising from the heater and then spreading throughout the room. And the third type of heat transfer, which is also used in the new Stirling engine, is thermal radiation. This also works in vacuum, so completely without air particles. This is precisely why we feel the heat of the sun on Earth even in the vacuum of space. So every body that is warmer than absolute zero, so minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, continuously emits electromagnetic waves. How much and what wavelength these are is determined by Planck's law of radiation. So this is also the reason why things emit light when they get really warm. But more important for us now is the thermal radiation in the infrared range. And at this point, we now return to our new Stirling engine and radiative cooling. What is special about the design from the UC Davis paper is that the upper plate of the Stirling engine is coated with a special paint or coating, as I mentioned briefly earlier. This paint ensures that the plate emits heat in a targeted manner as infrared radiation in the so-called atmospheric transparency window, which is between 8 and 13 micrometers in wavelengths. The Earth's atmosphere is particularly transparent to infrared radiation in this range. At night, when the sun is not shining and the sky is clear, this plate radiates its heat directly through this gap in the atmosphere, so through the window, out into space, which is about minus 270 degrees Celsius cold. The panel therefore emits heat directly in the form of radiation and can become colder than the surrounding air by that. The surrounding air, in turn, warms of course the panel slightly over time through convection, but the special coating or paint means that more heat is emitted than is returned by the air. The effect works best when there are no clouds and as little water vapor as possible in the air, because otherwise they reflect the infrared radiation, so it warms again. Well, and this physical trick creates a temperature difference between the warm underside, so the Earth, and the cold upper side, so indirectly outer space. And this difference can be 10 degrees Celsius or more, and that is actually enough to run the Stirling engine. And it is really impressive that it works at all with such a small difference, but this is kind of the magic of a Stirling engine. So in laboratory tests, Jeremy Monday's team was able to use it to operate small fans in greenhouses or generate enough electricity for small motors. The actual measured output in the field experiment was approximately 0.4 watts per square meter of radiating surface, enough to operate a small fan, for example, to circulate CO2 in a greenhouse. When used as a generator, there's even enough energy to power small electric motors and generate electricity. Theoretically, with even better materials and perfect heat transfer, over 6 watts per square meter would be possible. Okay, sounds pretty interesting, but of course there are some problems we have to talk about, and we always do this in the big hurdle of the video, also in this video. Before we get to that, please subscribe to the channel and activate the bell so you don't miss any more videos. And by the way, you can find all sources in the video description, and like in a scientific paper, I always display the number of the source in the video when I mention a fact, so you can always fact check me. Okay, let's get to the first big problem, and it is about the effect of this innovation, and it only works optimally on clear, dry nights, because water vapor and clouds block most of the heat radiation. Water vapor is a strong infrared absorber and by that closes this transparency window of the atmosphere. In addition, the output is still relatively low either way. In the laboratory, values of 0.4 watts per square meter are typically achieved. That's enough for a little air circulation, but it's still a long way from being enough for household electricity or large machines. By comparison, solar cells can often achieve up to 200 watts per square meter during the day under optimal conditions. Furthermore, there's a large discrepancy between the current laboratory output and the theoretical maximum of 6 watts per square meter. The researchers themselves say that the motor currently operates 15 times less efficiently than it could, mainly due to heat transfer losses and mechanical friction. The technology therefore needs to be developed further on a massive scale before it can become economically viable. And if larger applications are to be realized, huge areas would have to be coated with special material, which is also pretty expensive. Estimates range from $50 to $150 per square meter. Okay, and there's another point or problem or hurdle, and this is competition. So-called thermoelectric generators, or TEGs for short, and also thermal photovoltaic cells also generate electricity from temperature differences. Actually, I made a video about thermal photovoltaics a few weeks ago, and I will put it in the end card of this video if you haven't seen it yet. In short, thermal photovoltaic cells do not use the mechanical work of a piston, but instead they use a special semiconductor material to convert the Earth's infrared heat radiation directly into electricity. This works with a photovoltaic effect in which electrons are released and by that generate electrical current directly. This is therefore a purely electronic process that is intended as an add-on for normal solar cells. So let's compare these two. As I said, researchers have currently measured a real output of 0.4 watts per square meter in field trials for the Stirling engine. In a similar feasibility study, thermal photovoltaic cells have a power density of 2.26 milliwatts or 0.00226 watts per square meter. And like I said, with both technologies, there's a big potential for theoretical improvement, but of course this is always costly and it is not clear if somebody will invest in it, and by now it's just not so much energy. But for now this means that although the new Stirling engine is more complex mechanically, it provides stronger proof of concept for performance than thermal photovoltaic cells. Of course, if you want to generate electricity with the engine, you first have to convert it, but that is not the desired application here, because the movement can be directly used for ventilation, for example. And also generators have efficiencies of over 98%, so you could say that this is actually not a big problem. So well, as a conclusion, I think the idea is pretty clever, and I don't know about you, but I've experimented with Stirling engines quite a bit, both at school and during my studies, and I find it really exciting to give the whole thing a new twist. But to be honest, I do think for now it only has potential in a very certain niche, and this potential is probably not high enough to switch from PV and batteries. But we never know if this tech might have a comeback in the long term. I'm curious to hear what you think, so be sure to write your comments below and take care. See you next time, or as we say in Germany, macht's gut, you're Jacob. And by the way, here is another video I told you about the thermal photovoltaic cells.